And we're going to be talking about gas pressure, and this is on page 9 in the gases booklet. And pressure for anything is equal to force divided by area. And well, how are we going to measure, or what are we thinking about in terms of gases? Well, we know what we have. If this is the wall of my container, I'll draw it as a complete container. My gas particles are going to be bouncing off the wall, aren't they? And so the factors that influence how much pressure there is how fast these are moving, so there's speed. Now we do know from the ideal gas law that our gas particles move in straight lines and that they are high speed particles. And so for those of us, our physicists, we know that they're going to then hit the wall and bounce off at the appropriate angle, depending on what angle they hit the wall. And then they shoot off with a high average speed. Because obviously, here where they've changed direction, if we took the instantaneous speed there, it's going to be 0, isn't it? In that as they collide with the wall. But then they bounce off the wall without having lost any kinetic energy. So we remember that from our kinetic theory of gases. So they've got a high average speed. So the speed is one factor. The second factor is, well, how many? So if we've got lots of gas particles in there, then they're all going to be bouncing off the walls. But if we've only got a few, then there's going to be less particles bouncing off the walls, and the pressure will be lower. And then we've got the volume of the container. That's going to influence it as well. So if I have a set number of gas molecules or atoms in a 1 litre container, and then I transfer them to a 2 litre container, then they've got twice as much space as they had before. And so they're further apart and the pressure will be lower. What is going to be the biggest factor influencing the speed of the gas particles? Temperature. And so if we increase the temperature, we're going to increase the kinetic energy of the particles, aren't we? Now, did I talk about that in the... Yeah. And increasing, that not only increases the number of collisions, it increases the force of the collisions that it has with the wall of the container. Whereas these other ones will only increase the number of collisions, or, if we're increasing the number of particles, will increase the number of collisions. If we decrease the volume of the container, we will increase the number of collisions. But temperature here has those two aspects to it, where it's going to increase the force and frequency of collisions. Okay, so this is what we need to think about when we're thinking about pressure. So, in actual fact, what we've got here, this would be N, wouldn't it? The number of particles we will count in moles. Volume we're going to count as V in litres, like we've done before. And temperature, though, for all of our gas equations, we use Kelvin. Have I talked about Kelvin? Yeah. A little bit. Named after Lord Kelvin. Yes, and so this is very important. And of course, this is all for pressure. And as we look at on page 9, we can see that there are a number of different units that can be used for pressure. The Pascal is the SI unit. Now, it is the equivalent of 1 Newton of force acting over 1 square metre. It's actually a very small unit, and so most of the time we would express our pressures in kilopascals. So that's 1,000 times. It could also be megapascals or any other unit, and on your formula sheet you've got those prefixes that will remind you of the kind of scaling factor that you would have to use if there is a different unit. But kilopascal is 100% the most common unit of measure of pressure. And if you watch the news and watch the weather and they're talking about pressure, sometimes they talk about hectopascals, but they also talk about kilopascals as well. Now, the other measure of pressure is atmosphere. And so it's just in atmospheres. So 1.00 atmosphere is basically the atmosphere at sea level. And 1 atmosphere, which I've already written here, is equal to 101.3 kilopascals. So you can see that 1 atmosphere, which is the amount of pressure from the gas above us, all of the weight of the weight force of the gas molecules above us, pushing down on us, is 101.3 kilopascals. It's actually a lot of pressure. Now, we don't notice it because this is where we live, and this is normal for us. And in fact, low pressure would be a problem for us. You know, like, I don't know if you watch any of those sci-fi movies where the astronaut gets a hole in their suit and then they're exposed to no pressure of space, and then their eyes explode, and, you know, of course, their eyes pop out of their head, and basically it's partial turning inside out happens, as all the things that are just held in fairly softly, or need to be pushed in by the atmosphere. If without that there, they can just get pulled out. And that's true. So we need that pressure for our bodies. But we also don't want crushingly high pressure. Where do you think we can experience really high pressure?
Ocean.
Sorry? Ocean, yeah, underwater. So if we go down, and in fact, we've been able to explore more of space than we have of the deep sea trenches because of the problem of pressure. That you need to be able to have the vessel able to not get crushed. There have been a few incidents with submarines, and even with the Titanic that sank a long time ago, over 100 years ago, it took a long time for technology to be able to go down and have a look at the wreck, because it's so deep. I think it's something around about 4 kilometres deep where the Titanic ended up. So high pressure and low pressure are not real good for us. And then the other one is millimetres of mercury. And 760 millimetres of mercury is also equal to 101.3 kilopascals. All of these are on your formula sheet. So if you have a look at the front page of your formula sheet, you should be able to see that these are all listed on there. Just to remind you of these three different ways that we can measure pressure. And on page 10 there is a little bit of some practice on converting. Now I'm just going to rub this off, and I've got a little bit that I'll write up about. Don't worry if you didn't get it all down, because you'll be able to just fast forward me on to the right part and then just pause and sort of be able to see it there. So this, just in case this wasn't clear, the molecules are that move up the atmosphere. So we know, what would we class the atmosphere as? I reckon I'd class it as a mixture. So do we know what air is made of? What's the main gas in air? Nitrogen. Isn't that a good thing? Seeing it's not flammable really helps us. Because when we light a fire, we don't explode, or we know what 100% oxygen atmosphere is like, don't we? So it's good for our health. We're made for this place. Now, I've said to you before, I believe, that we know that our gas particles are high energy particles and that they spread evenly within their container. But when we think about the atmosphere, if this is Earth, then most of the gas is actually close to the Earth's surface because of that gravitational attraction. And as we move further away from the Earth, we go through the different, the troposphere and the mesosphere and all the ionosphere, etc., until we enter basically space. And the ISS is 400 kilometres, it orbits 400 kilometres above the surface of the Earth, and that's essentially space. So yes, they're evenly distributed, but they're also, because they are particles, they are also attracted to the Earth, and so we have this greater density of particles close to the Earth, which is why we have to qualify when we're talking about pressure that we're thinking about sea level, because even if we're on a mountain, we're going to have lower air pressure. There's going to be less density of the molecules, and if you want to climb Mount Everest or something like that, you either have to go through a lot of training, or you carry oxygen with you to be able to breathe. Just because, there's less molecules of air all around, you're going to find it hard to breathe. The people, the indigenous people, the Tibetans, for example, can cope with it because they have been born in that area, in that region, and they develop enough red blood cells to be able to cope with it. But even the people who would act as Sherpas, who carry gear, etc., it generally takes a big toll on them too. They wouldn't normally undergo that kind of activity. Mount Everest is a sacred spot for them, and they don't like necessarily that people are trudging all over it, but they do it because they need money for their families. So that's pressure. Let's have a look at that. I'll stop there for the moment so that you can do those questions on page 10.